Now, let us see the next application of electric field due to a continuous charge distribution for a disk. Electric field due to a disk. Electric field due to a uniformly charged disk. Let us say this. Now consider a disk like this. This is uniformly charged. This is uniformly charged, whose radius is r, at a distance on the axis, at a distance x. Let us find out the electric field due to this charged disk. Let us see now, consider a small element of the disk. Due to that element we will find out the field first, then we will integrate it so that you will get the total electric field due to the charged disk. Now consider a small ring of charge dq and of radius r, whose thickness is dr. Then we already calculated what is the electric field due to a ring upon its axis. The electric field due to the ring is dE because of the charge dq, dE on its axis at a distance x is k, elemental charge is dq, distance is x, by r square plus x square whole power 3 by 2. This is what we have written for a small ring. For a ring, okay, here for the small ring that I have manipulated the same values of ring. Now here, what is this dq? What is this dq? So dE is equal to k. dq is, since it is for charge density, surface charge density, I will write it as sigma is equal to dq by dA. dq is equal to sigma into dA. So dq is equal to sigma, surface charge density, into dA is 2 pi r is the circumference of the ring and dr its thickness. So this gives the small area of the element, this electrical element. Sigma, surface charge density, and dq is the charge of the elemental ring. So from this, if we substitute this here, what we will get? So dE is equal to k into x. I will write sigma 2 pi r into dr by r square plus x square whole power 3 by 2. So now the entire function is in terms of this distance r and a fixed distance x. If this elemental ring varies from 0 to r, then we will get the total charge distribution of the disk, and the electric field can be calculated at this point at a distance x on its axis due to the entire charged disk. Okay, now let us see. So for the entire field due to the charged disk upon its axis, I will integrate it on both sides. Integral of dE will give E, which is equal to integral of k sigma 2 pi x into r dr by r square plus x square whole power 3 by 2. So these are constants, will bring out of integration. So 2 pi k sigma into x integral of r dr by r square plus x square whole power 3 by 2. Now we will see the integration of this one. So now I am considering r square plus x square is equal to t, 2r dr is equal to dt. Now E is equal to 2 pi k sigma into x integral of r dr is dt by 2 by t power 3 by 2. So this can be written as this 2 will get cancelled out. Pi k sigma into x integral of t power minus 3 by 2 into dt. So I can write this as pi k sigma into x t power minus 3 by 2 plus 1 by minus 3 by 2 plus 1. So E is equal to, this can be minus 1 by 2. So minus 1 by 2 means minus 1 by 2. 2 will go up, 2 pi k sigma into x into t power minus 1 by 2. So I can write it as E is equal to minus 2 pi k sigma into x by root t. So t value from here I can substitute as E is equal to minus 2 pi k sigma x by root of r square plus x square. Now this r is variable from 0 to capital R, which gives the total entire disk, charged disk. Now let us see that. So E is equal to, finally the equation, minus 2 pi k sigma x into 1 by root of r square plus x square from 0 to r. So you'll get the final equation of the electric field due to a disk as basically upper limit minus lower limit. Here minus is there, therefore I am writing as lower limit minus upper limit. So 2 pi k sigma x, 1 by substituting 0 you will get x minus substituting this r, 1 by root of r square plus x square. So the final equation for the electric field due to a charged disk upon its axis at a distance x having a radius r and charge q is given by E is equal to 2 pi sigma by 4 pi epsilon naught into, I am sending this x inside, 1 minus x by root of r square plus x square. 2 pi 1s are 2 pi 2s. Therefore E is equal to sigma by 2 epsilon naught into 1 by 1 minus x by root of r square plus x square. This is the electric field due to a disk upon its axis. If the disk is an infinite disk, then from here 0 to infinity, then for an infinite disk, integrate equation from 0 to infinity, then the electric field due to infinite disk can be written as sigma by 2 epsilon naught. We have discussed the electric field due to the distributions like the ring and the disk, and other distributions will be discussed after the completion of electric flux and Gauss law, because which will be very comfortable for us using the Gauss law describing the electric field due to other distributions. Now we will see the concept of dipole. What is this concept of dipole? What is this dipole basically? Dipole. Di means 2. Di means 2. Here, two charges of equal magnitude and opposite polarity separated by a certain distance constitute a dipole. That is minus q and plus q. These are the two charges of equal magnitude but of opposite polarity separated by a distance. Let the center of the dipole is notified like this. The distance of this charges from the center is A and A. The length of the dipole is 2A. Now the dipole is defined as basically two charges of equal magnitude and opposite polarity separated by a certain distance constitute a dipole. Every dipole is characterized by a property called dipole moment. The dipole moment magnitude is given by the product of the charge and distance between the two charges. The product of any one of the charge and distance between the two charges, which is known as dipole length. So this is the magnitude of the dipole. The dipole moment is a property of a dipole whose magnitude is given by the product of any one of the charge of the dipole and its dipole length. Dipole moment is a vector quantity. Dipole moment in vector form can be represented as P bar is equal to Q into 2A bar. Q into 2A bar. The direction of this vector is always from negative charge to positive charge. This will be the direction of the dipole moment of a dipole. What is the unit of this dipole? Unit of this dipole moment. So Coulomb meter. Coulomb meter is the unit of dipole moment of a dipole. Electric field due to a dipole. Let us see the electric field due to a dipole. So electric field due to a dipole. Electric field due to a dipole. On the axial line. On the axial line. On the axial line. What is this axial line? Let us see. Take a dipole of dipole length 2A, whose distances from the center of the dipole are A and A. Axial line is a line that passes through the center of the dipole along its dipole length. Now I say this is the axial line. This is the axial line. Now to find out the electric field due to a dipole on the axial line, consider any point, say M, at a distance x from the center of the dipole. X from the center of the dipole. Now, electric field due to the positive charge at this point is in this direction due to positive like this, because away from the charge. Electric field due to negative charge will be like this. I am representing this as E minus. Since the two charges are of equal magnitude and positive charge is very close to M than that of negative charge, the electric field due to this one, that is positive charge, will be greater than that of negative charge. So the net electric field due to positive and negative charges will be away from the dipole. Away from the dipole, that is in the direction of dipole moment. In the direction of dipole moment. Let us see what is the net electric field. Net electric field will be is equal to E plus minus E minus. So net electric field will be equal to, so this distance, the distance of this M from positive charge is x minus A. From the negative charge is, this is the distance, this is x plus A. So x plus A. So electric field is kq by x minus A whole square minus kq by x plus A whole square. These are the two fields due to positive and negative charges, and the resultant field is given like this. Now E net is equal to, so kq is common. I am making this x plus A whole square minus x minus A whole square by x square minus A square whole square. Now what is the net electric field? Now the net electric field is given by kq into A plus B whole square minus A minus B whole square is 4AB. So 4x into A by x square minus A square whole square. Then this, we know that the dipole moment is q into 2A. On substituting this over here, we will get E net is equal to k. From this 2A into q gives dipole moment P. So but next the remaining is 2 into x. So this is 2x by x square minus a square whole square. So therefore, the net electric field due to the dipole is given by 2 kp into x by x square minus a square whole square. So this is the net electric field. This is a net electric field. Now, if the dipole is very short, that is, the distance of the point where you want to find out the electric field on the axis is too large than that of the dipole length. That is a short dipole. We can discuss it as a short dipole. X is 2 greater than a. Then I can write the electric field due to the dipole on the axial line as 2 kp into x by, this a can be neglected, I can write it as x power 4. Net electric field due to the dipole is 2 kp by x cubed. So this is the net electric field on the axis of a dipole in the direction of the dipole moment due to a short dipole. Now electric field due to a dipole on its equatorial line. Electric field due to a dipole on its equatorial line. Equatorial line. What is this equatorial line? Let us see, draw a dipole. So this is minus q, one positive charge, one negative charge and one positive charge. These are the distances from the center of the dipole of the two charges. Equatorial line is a line that passes through the center of the dipole perpendicular to the dipole length. Equatorial line is a line that passes through the center of the dipole and perpendicular to the dipole length. Or you can also say the equatorial line is a line that passes through the center of the dipole and perpendicular to the axial line. Now consider a point M at a distance x from the center of the dipole. Now the net electric field due to this dipole at this point on the equatorial line is given as, now electric field due to the positive charge is away like this. Electric field due to positive charge is like this. Electric field due to negative charge is towards the charge, which will be like this. Electric field due to negative charge. This is the distance x and this is a and this is a. Then this angle will be definitely equal to this angle. And this distance of will be x square plus a square. And this distance also x square plus a square. Now the electric field due to this charge like this. Electric field due to this negative charge will be towards. Now if I draw a line here, if this is theta, this will be theta, alternate opposite angles. If this is theta, this will be theta, corresponding angles. So now I can write the net electric field will be like this. There will be two components for E plus and E minus. One component will be like this and one component will be like this. Due to this E plus, one component will be like this and this component will be like this. From here we can understand E plus is equal to E minus, which will be equal to KQ by x square plus a square. The electric field due to the positive charge at this point and electric field due to the negative charge at this point, both are in equal magnitudes. Okay. Now the two components towards left side will be E is the two components will get added up. E net is equal to E plus cos theta plus E minus cos theta. Other two components, E plus sin theta and E minus sin theta, will get cancelled out because E plus is equal to E minus. So from this we can write E net is equal to 2E plus cos theta. Therefore, the net electric field on the equatorial line of a dipole can be written as 2kq by x square plus a square into cos theta. Cos theta is adjacent side by hypotenuse, that is a by root of x square plus a square. Now the total net electric field can be written as kq into 2a by x square plus a square whole power 3 by 2. Now this q into 2a is called the dipole moment of this dipole. So E net is equal to, so kp by x square plus a square whole power 3 by 2. X square plus a square whole power 3 by 2. This is the net dipole, net electric field due to a dipole moment P on the equatorial line. And if we observe, the net electric field is opposite to the direction of dipole moment. The net electric field is opposite to the direction of dipole moment. If we write this in vector form, we will get negative symbol. So no need to worry about that. Okay, E net is opposite to the direction of the dipole moment of the dipole. Okay, this is the net electric field. So if the dipole length is very small when compared to distance of the point where we want to find out the electric field, x less than a, then the net electric field, x is 2 greater than a, then the net electric field would become, a can be neglected, kp by x square whole power 3 by 2. This one gets cancelled. E net is equal to kp by x cubed. Kp by x cubed. So this is the net electric field on the equatorial line. Now this I am representing as on the equatorial line. We already know that electric field on the axial line is 2 kp by x cubed. So therefore from these two we can write electric field on the axial line is 2 times the electric field on the equatorial line. So this is what the electric field due to a dipole on its equatorial line. Electric field due to a dipole at an angle theta to the direction of dipole moment. Electric field due to a dipole at an angle theta to the dipole moment. Let us consider a dipole minus q and plus q. Here the distance between them is 2a. Now I am considering a position vector. Here a point is being taken which is at an angle of theta to p bar. This is the direction of p bar. This is the direction of dipole moment. To this direction I am taking an angle theta at a distance x where we want to find out the electric field due to this dipole. Okay. Now at this point, now what I do is this dipole moment is divided into 2 parts, one like this and one like this. This is p bar, which is p cos theta. This is p sin theta. For a dipole of dipole moment p cos theta, this point is on the axial line. For a dipole moment of p sin theta, this point is on the equatorial line. This is the dipole moment p sin theta, which is on the equatorial line. So because of p cos theta, the electric field will be like this. I will say it as axial line. Because of p sin theta, it will be opposite to the dipole moment p sin theta, like this. The net electric field would be somewhere like this in between. Let us calculate the electric field on the axial line. Because of p cos theta, the electric field on the axial line, this will become p cos theta, dipole moment, and this point is on the axial line at a distance x. Now I write it as k 2kp cos theta by x cubed. Electric field on the equatorial line. we know that this is the dipole moment P sin theta, for which this point is on the equatorial line. So then I will write this as EE. So that EE can be written as KP sin theta. Here P sin theta is the dipole moment for which this point is on the equatorial line. That is why I have written EE, KP sin theta by x cubed. The net electric field, these two are perpendicular. So the net electric field would be root of EA square plus EE square. Since the angle between these two is 90, so EE is perpendicular to EA. So therefore E net is equal to KP by x cubed into root of, in this 4 cos square theta, 1 cos square theta plus sin square theta will become 1. So balance is 3 cos square theta. Then I will write it as 1 plus 3 cos square theta. So this is the electric field here. What is the direction of the electric field? What is the direction of this electric field? The direction of this electric field can be understood from here. Let this angle is alpha. The direction of electric field at M, that is at an angle theta to the dipole moment, is given by tan alpha, where alpha is the angle made by the resultant electric field or the net electric field with the electric field along the axial line. So tan alpha is equal to, I will show you here, this is EE by EA, EE by EA, that is EE by EA, opposite side by adjacent side. Therefore tan alpha is equal to EE is, which is here, EA is, which is here. If you cancel them, KP by x cube gets cancelled. Sin theta by 2 cos theta. So tan alpha is equal to tan theta by 2. So this is the angle made by, the resultant electric field with the position vector. That I can say you, this is a position vector.